Thanks, Alvin. So I think 5 years ago there was a CaJAGWR meeting here at Caltech, and I presented one of the first problems we had to overcome to do nonlinear perturbation theory. So it's nice to be back and actually present a complete result, although I didn't think it would take 5 years to get back and do so. So the result I'm presenting today is in collaboration with Adam Pound, who's at the University of Southampton, Barry Waddell, who's also at UCD, and Jeremy Miller, who was a PhD student in Southampton. And some of the gory details are based on this paper, which recently was just accepted last week for publication in PRL. Okay, so just to start, just very quickly to remind and refresh, just in case it wasn't clear, we're modeling extreme mass ratio inspirals. These are binary systems where the mass ratio is very small. So I'll consider the mass ratio to be small, not large as they do in numerical relativity, because I wanted an expansion in that parameter. The primary is typically a massive black hole, and the secondary will be some compact object, and we require it to be compact so that it doesn't get tidally disrupted in the strong field of the massive black hole. And so for LISA, the typical kind of mass ratio range is 10 to the minus 4, 10 to the minus 7, that sort of range. And the key features are these are LISA sources. They're the millihertz gravitational wave sources of this mass ratio. And you typically get tens to hundreds of thousands of orbits deep in the strong field around the black hole. That's one of the unique things about these sources. And they will tend to be visible for months or even years in the LISA detector. So you might turn the detector on and you might see a single emery for the entire duration of the mission. They're also very generic. There's no expected spin alignment, so they'll be fully processing. And there's also considerable eccentricity. This is a movie made by Steve Drasko that shows an example of what an emery would look like, and it's showing the trail over a few days. And so typically eccentricities can be as high as 0.7. So it's a complicated system. But of course, that complication leads to a very rich waveform phenomenology, which carries with it lots of information. So this is an example of a waveform, and you can see it has lots of features. As the particle goes in and passes through periastron passage, you get these bursts, lots of features from the precession of the orbit. What can we do with emeries? What is the science deliverables? Well, let's suppose emeries exist, that LISA is flying, and that we have accurate waveforms. That's obviously the goal of my talk. But just to paint the big picture, what can we learn about the universe? We can broadly fit this into two categories: astrophysics. So we can measure the mass of black holes to very high accuracy, and their spins, as well as spin on the secondary. This can then teach us about dense stellar clusters around black holes, massive black holes. So if you look at, for instance, if you find them very high eccentricity, you expect that these emeries probably form through direct capture. If you find them with low eccentricity, they probably form through tidal disruptions of binaries. So it tells you about the environment in which these massive black holes live. And also, we can do surveys of massive black holes and the nearby universe. We can tell you about structural formation. If the massive black holes are rapidly rotating, we probably expect they grew through gas accretion. If they're not, probably through mergers. The other big promise of emeries is doing fundamental physics. One of the key things that emeries are kind of one of their shining examples is measuring the quadrupole moment of the space-time. So if you can measure the mass and the spin, and then from the no-hair theorems you can calculate the quadrupole moment, you can then measure that independently, and you can check, is the object the massive black hole? Is it really the black hole of Einstein's theory of gravity? So that's one of the key things we want to do with emeries. There's some other stuff as well in terms of testing propagation of gravitational waves, testing for beyond standard model physics of massive fields around massive black holes, measuring the Hubble parameter and so on. So there's a lot of stuff we can do with emeries. What I want to talk about really is how do we get these accurate waveforms, and I'll talk about how accurate they need to be in order to do the science that we want to get out of LISA. Okay, so we're doing black hole perturbation theory. So what we're going to have is a massive black hole of mass capital M. It's going to be orbited by a smaller body of mass little m. And the basic idea is pretty straightforward, and the details are obviously very complicated, is we expand the mass of the binary, the metric of the binary G, about the metric of the massive black hole. So we'll take this to be the Schwarzschild or Kerr metric, and then we'll add first-order corrections, second-order corrections, or in principle, as many as we have strength to continue making the calculation. We'll then just substitute this into the Einstein equation, and then expand out and solve order by order. One other thing we'll do is, at least at first order, we consider this small body here to be a point particle. So we choose it to be modeled as a delta function moving along some representative world line. And then we just expand. and we just do perturbation theory. So we can expand the Einstein tensor. We have some leading order piece, some first order correction, and some second order correction. And so a lot of my talk is going to be talking about particularly how we calculate the pieces that appear here, and how do we make sense of things that appear at second order. Once you have the perturbations to the metric tensor, you can then take some derivatives of them and compute something called the self-force. There's a regularization step, which I'll briefly mention. And then you use that to drive the inspiraling motion. So you have the force geodesic equation. And we call it the self-force just because it's the metric perturbation back reacting onto the smaller body. Okay, so I did an expansion there, but why did I stop at second order? Why did I not need first, or why do I need to go third? That's obviously a key question when you're doing any sort of expansion. How far do I actually need to go? So over the inspiral timescale, the phase of the gravitational wave, which is the key thing for doing gravitational wave science, scales in the following way if we ignore resonances, which are a special case. The phase has some leading order contribution that scales as epsilon to the -1. This makes sense. As we go to the test body limit, the particle never plunges, it just sits there forever. There's then some subleading correction on epsilon to the 0, and then in principle higher order corrections, but we don't need those for Emery science. So this leading piece we call the adiabatic order. And this is the stuff you're probably familiar with. If you know anything about this at all, this is the stuff that comes from solving the Tucholsky equation, computing fluxes. And what's nice about this is that this is related to the local metric perturbation. You just need the orbit average piece of that, and this can be related to the fluxes via flux balance. And what's great is that gives you most of the phase. You get the first 100,000 radians. Great. And this is good enough probably for detection of some sources and maybe rough parameter estimation for particularly bright Emrys that happen to be out there. But you're still going to be losing of order epsilon to the 0. So we don't know the coefficient. It could be 1, could be tens or hundreds of radians. And we know if we're doing match filtering techniques, that's going to really mess up your data analysis. So to do the really precise science and to get the full potential of LISA, we need to compute this subleading correction. So this is, understandably, called a post-adiabatic order, of which there are 3 contributions. There's 2 pieces from the first order self-force, specifically the oscillatory pieces that don't appear in the average. And then there's a piece of the second order metric perturbation that appears in here. And so you need to include this in order to extract all the sources we might hope to have in LISA. And the precision test of GR that I talked about, being able to really nail down what the quadrupole moment is of the massive black hole, that really depends upon having these higher order corrections. And the potential application for Imry's intermediate mass ratio inspirals, because if you look at the residual, okay, I don't know the coefficient here, but let's say it's small, then if I have a mass ratio of 1 to 100, the error in my waveform phase will be 100th of a radian. So you jump from having hundreds or tens of radians by not having this term to having 100th of a radian. It's quite impressive. And of course, we don't know what that coefficient is. We'll only know when we finish this calculation and then compare with numerical relativity, say. But there's some hope that you might be able to cover a large part of the parameter space, and in particular, these are very difficult sources to model in numerical relativity. Mass ratio 1 to 100, 1 to 1,000, very challenging. Okay, so just where are we in the state of the art? What sort of stuff has been done? So this leading on dissipative piece, as I said, is basically been done since the 70s, at least for circular orbits around a Kerr black hole. So you've been able to compute the first 100,000 radians for a long time. For fully generic orbits, as we expect Emrys to be, with eccentricity and full precession, this is kind of wrapped up in 2006. There's another work with a Japanese group. Although I must say there's no systematic exploration of that parameter space yet. That's work that we're currently doing. These subleading corrections, the self-force corrections, the foundation of that was laid in 1997. Is how to even calculate this, and then it took another 10 years to actually make those calculations in just for circular orbits in Schwarzschild spacetime. And then just 2 years ago, Martin van der Ment completed this program, and we now have the self-force, the first order metric perturbation, the first order self-force for fully generic orbits in Kerr. And the subject of this talk is then how do I compute things at second order. So we don't yet have the dissipative piece, the thing you actually need for the waveform. What we do have is the binding energy, but as I'll talk about, in order to calculate that, we've computed about 90% of all the stuff you need to compute this. In fact, we're very close to having this, we think. Okay, so now we have to go into some details. This is perturbation theory. So this has been a long calculation. There's a lot of details. I'll point to papers if anyone's interested, but I'll try and give just an overview of how this is done. So bear with me. Okay, so as I said, we expand the metric of the binary. in powers of the mass ratio. We stick it into the Einstein equation. And then we just look at what happens order by order. So leading order, very straightforward. Just have the Einstein tensor acting on a background metric, which is a vacuum solution. So 0 on the right-hand side. At first order, this is what people have been doing for decades. We have the linearized Einstein operator acting on the first order metric perturbation sourced by the point particle source. This is what people are familiar with. And at second order, what you get is the linearized operator now acting on the second order metric perturbation. Plus, because Einstein's equation is nonlinear, we have contributions that come from products of first order metric perturbation. Okay, so just to simplify notation, so these are the linearized Einstein equation. Leading all this is just the usual kind of wave equation, and then at least in the Lorentz gauge, with some subleading corrections. I'm going to stop calling it G1 and just call it box, just to simplify notation. I'm also going to drop alphas and betas everywhere again, just to stop carrying that around. We know that these things are tensorial objects. And I'll throw away the zeroth order piece. I mean, that's easy. Okay, so these are the equations we want to solve, right? So what we really want to do is solve this for the second order metric perturbation. So first, easy step, just move this to the right-hand side. Now, the second order metric perturbation is now sourced by this second order Einstein tensor made up of products of the first order piece. Now, that's obviously a very simple manipulation. Just running it down list, it turns out this isn't well defined. There's some products of distributions in there. And so what we have to do is regularize this equation. And so what we do, and this is a very common thing we do in self-force calculations, is we split the metric perturbation into a regular piece, a piece that's responsible for the self-force, whose derivative gives us the motion of the body, and some puncture field, which captures the divergence of the metric perturbation, but in no way contributes to the motion. And so, because this is a linearized operator, I can act on two of these, and I can move this piece to the right-hand side. And this will act to regularize this. That's basically how it's constructed. Okay? So just to say, this is the usual point particle source. This is our usual wave operator. Of course, the real crux of this calculation is what is that thing, right? Like this is easy to write down and say, there's something wrong here. I need something that corrects it. And this was, the formulation for this was written down in 2012. There's two papers. We worked with the formulation by Adam Pound, but also Sam Gralla in the same year produced a formulation. It's cut off here, but there is a reference. Okay, so we need to understand what that is. What does this thing look like? Well, this is a non-compact term, which is a big challenge over what you have at first order, where everything is compact. It's just defined on the world line. This thing is now non-compact, and it also diverges of the particle, which is cancelled by this. And so what I want to kind of go through is talk about how do we actually compute these pieces in practice. As I said, the equations of motion take this form. We're here being a little more explicit in saying, well, this first order self-force is dependent on the regular metric perturbation, and this second order self-force is dependent on the regular, second order regular metric perturbation. Great. So we have the equations. This was written down in 2012. What's the problem? Well, one of the challenges with the way it's written here is that, an additional challenge comes from the fact that this puncture field is written in the Lorentz gauge. And unfortunately, we have never managed to stably numerically evolve the Lorentz gauge perturbation, even at first order metric perturbation. So given we can't do it at first order, we definitely don't want to try it at second order. So we don't want to solve these time domain equations, these PDEs. Now, there's other reasons you might not want to do that as well. Even if you could solve those PDEs, you'd have to evolve an inspiral with 100,000 orbits, and that would give you one waveform. Right? So this isn't a practical way of filling out any parameter space. So you probably want to do something else anyway, but even if you could, we can't do it at all. We don't know how to numerically stably evolve it. And so the next step in kind of massaging the equations is to do a 2 timescale expansion. And so there's 2 parts to that, of the motion and of the equations, the field equations. So hereafter, just to keep things simpler, and it's because of the work we've done, we'll just focus on quasi-circular orbits in Schwarzschild spacetime. So neither the primary or secondary is rotating. So the world line is then just given by T, RP, the position of the particle. We'll specialize just the equatorial plane as usual, and the azimuthal phase. And there are two timescales in the binary. There's the radiation reaction timescale, over which the binary kind of slowly evolves, and there's the fast orbital timescale. And so we'll choose our slow time in our 2 times expansion to be epsilon times coordinate time, and our fast time to be the azimuthal phase. It varies on the orbital fast time. The radius and the orbital frequency evolve on this slow timescale. So we can expand these out as a 0th order piece plus first order corrections. And likewise with the frequency. We have a 0th order piece of the frequency plus first order correction. And then to get the equations of motion for what these objects, we just substitute these into this equation. There's a full expression for this. And this gives us equations of motion and tells us how the frequencies evolve and how R0 and R1 evolve. And it tells you this is the usual frequency you're used to for circular orbits. Omega 1 then has a contribution from the first order self force, and this R1. R0 just evolves according to the dissipative piece of the first order force. These are the usual adiabatic inspirals people have done for decades. And then the key thing is R2, the second order piece, the expansion. So the second R1, the first order piece here, is dependent on the second order metric perturbation. Okay, so the equation of motion, those are pretty straightforward for quasi-circular. Perhaps more interesting is the field equations, which allow us to finally massage things into the form we want. So here, we're going to expand the metric perturbation as we typically do. We'll make use of the fact that we have spherical symmetry. So we'll expand the metric perturbation in tensor spherical harmonics, to some basis. We'll then factor out the radial piece, and then we'll do a decomposition in time, ETI omega phi, with the phi we're treating as a time parameter. We're also going to expand our box operator. You recall this was dt squared. We're now doing a 2 time scale expansion, so time is a function of these, the slow time and the fast time, is t. This changes this operator in the following way, just using the chain rule. So here you've got a dt by dt tilde by dt, which gives you an epsilon from here. Likewise, you get a d phi by dt, gives you this omega. The upshot then is that you expand this operator when you drop into the frequency domain into a leading order piece plus a subleading correction, where, losing a bit of it, but the leading order piece is just what you're used to. If you solved a Reggie-Wheeler equation, it's just a second R star derivative minus the omega squared term. And the subleading piece, you get an omega 1 appearing plus a d by d slow time. This is a t tilde here. And the omega 1 comes from expanding this object. So this is omega 0 plus epsilon omega 1. This just gives you the order epsilon piece that appears here. So when we drop into the frequency domain, the equations we had before, this is just exactly what I've written down before, but we've dropped into the frequency domain. And then finally, when we expand out this operator, we expand these box operators. What we get from here is we get an epsilon, this term, the box 1 omega, hitting h1, and that's obviously a second order term, so that then appears on this line. So this then gives you the final form of the equations. So you have the normal operator you've been used to solving, the leading order box operator in the frequency domain, here and here, but then you get this first order operator appearing, and this is a second order contribution because of this epsilon and hitting this h1. So these are the equations that we go ahead and solve. And just some terminology if I hadn't mentioned already, this thing here on the right-hand side is called the effective source. And so the name of the game now is to construct this object, and then once you have the source, this is just an ordinary differential equation. We know how to find solutions to ordinary differential equations. Okay, so I'll just go through these 3 terms and discuss how we actually compute those in practice. So this first term, the second order Einstein tensor, that's an easy thing to write down. You just ask exact, so expand Einstein's equations up to second order. The challenge is we have to decompose everything into modes. So here I've dropped the LM indices, I should say, just got the omega left. So we need to expand the second order Einstein tensor into modes. And also in principle, we've computed these first order modes also for a mode decomposition. So we have products of first order modes, and then we're trying to do a mode decomposition, so we get triple products of YLMs that we then have to integrate against to compute the mode contribution to this object. So we end up with some big coupling formula that couples all these things together. The problem we have, though, is that we only have finitely many numbers of the first order mode. We have to compute these numerically. We don't have an analytic solution in this case. And we need to have, in some sense, an infinite number because there's a divergence in here that must cancel this divergence that appears here. And so it's not enough just to do it numerically. We have to do something a bit cleverer. So what do we always do when we do, well, okay, here's an example. This is in this paper by Jeremy Miller and Barry and Adam. If you just add more modes, you can see you're getting closer to having the divergence, but of course you'll never actually fully get it, right? But you need to be able to cancel this against some divergent thing here. So what do we always do? In self-force calculations, we split it into a regular and a singular piece. So we split H1 into a regular piece and a puncture field, and then we can re-expand this object into a piece that has products of p fields, of the puncture field, the singular piece, products of the puncture field and the regular field, and products of the regular field. So these two terms will converge reasonably quickly, so you can just put in numerical pieces. This term is completely analytic, at least in principle, and you can compute that. And so that is how then you can compute this object, and it's fully divergent. Capture the full divergence here. Okay, so we can go ahead and do that. So here what I'm showing is this object for just the monopole mode, the L equals 0 mode of the metric perturbation. As I said, it's made up of coupling between the first order metric perturbation, so it's non-zero everywhere in the space-time. Here we have a particle at 8m. This is the divergence you can see. These are not divergences, these are just zero crossings because this is on a logarithmic scale. And so you can see this object, this is us having computed this now. So we did this quite a while ago, and one of the first things we noticed is it doesn't actually fall off fast enough to make this source integrable. So I'll just say a little bit about that. So what we do is that we observe that second order Einstein tensor falls off too slowly. And this basically comes about because, well, one of the reasons it comes about is at first order, your metric perturbation you've been computing, it's sourced by the geodesic, which is just sat there forever, eternally, going around and around. And so your space-time sourced by that metric perturbation is now just flooded with radiation. You just kept it going around forever. That's what this H1 is. This leads to problems at the boundaries. You've lost asymptotic flatness. We've got coupling between the modes as well, making it worse. And so I'm not going to go into details at all, but Adam went through this. And what you do is you match your kind of near zone near the particle onto some physically correct post-Minkowskian expansion to deal with this. So you get some divergences you don't want, but we know what the correct solution is, and so we can do some matching procedure and correct it. So just to say that what this does is this introduces some extra additional punctures, some extra things we have to do near the horizon and near infinity. So in terms of actually computing this source, what this does, we now get the yellow curve, so nothing changes near the particle, but we match onto some behavior near the particle, near the horizon, which is well behaved, and some behavior at infinity, which is well behaved, which makes this thing integrable. So just another technical detail. Okay, so we've dealt with any issues we have at the boundaries, but of course the main challenge is near the particle. For that, we need to understand what this second order puncture is. Okay, so again, I won't say too much details here. This is a kind of commonly done thing in self-force, so the details are pretty complicated at second order. What we do is we do a matched asymptotic expansion. You imagine that near the small body, this is just a Schwarzschild black hole which is tidally perturbed by the big black hole. Likewise, if you zoom out, the big black hole looks like a black hole which is tidally perturbed by the presence of the small body. And by having some overlap region, some buffer zone, we can perform a matching procedure, and this will give us the equations of motion and what the puncture field is in this case. When you do a mode decomposition of that object, you'll find that it diverges logarithmically at the particle, but that's exactly what you want because it will cancel the divergence that appears in this term here. So there's a lot of steps here. You have to actually compute this thing. The paper that's referenced here gives you a fully covariant form for that. You then have to then break covariance, put it in a particular coordinate system, do a mode decomposition. In fact, the mode decomposition is particularly hard, and that's the one piece that's now holding us up in the calculation. But when you do that, what you find is that you can cancel off the divergence at the particle and end up with something just smooth and regular. And so now you have a source, at least these two terms, which is smooth and regular across the whole spacetime and integrable. Okay. So So one more term to deal with, which is the slow time derivative term, the time that appears into the 2 timescale expansion. So a few things to note here. So another challenge at second order is that at second order, it's sourced by the first order metric perturbation, which is the body is in principle slowly inspiraling. So the mass of the central black hole is given by some initial mass plus some growing piece, which grows over time as it absorbs energy and angular momentum in the gravitational waves, in the radiation. Okay, so our first order metric perturbation is dependent upon this delta m and delta j, as well as obviously the radius of the particle. If you recall, this box operator, box 1, the frequency domain slow time derivative term, is linear in this quantity. So how do I actually compute this slow time derivative with respect to of the metric perturbation h1? Well, just appeal to the chain rule, and I get derivatives of delta m and delta j with respect to slow time multiplied by these, and then a derivative of the R0 with respect to slow time. So that's just the usual inspiral we're used to calculating at leading order. And then that slow time derivative is then replaced by a derivative with respect to R0. So I need to compute the metric perturbation everywhere in the spacetime and its derivative with respect to the orbital element everywhere in the spacetime as well. These two terms are pretty easy to compute as well. They're just proportional to the energy and angular momentum flux into the horizon. It's just the rate of change of the mass and the angular momentum of the black hole. And as I said, this term here, we just need to calculate, this is quite hard, to calculate the derivative of the first order metric perturbation everywhere in the spacetime with respect to R0. And of course, as this is derivative of the first order metric perturbation, this is another non-compact piece that has to be added onto the calculation. So as you're going through this, there's a lot of foundational challenges, but there's also a huge amount of data that accumulates, because I have to store the metric perturbation in all of its modes everywhere in the spacetime in order to compute all these various things. This is just a small point that will come up a little bit later on, but at any particular instance of slow time, we can set delta m, delta j, and omega 1 to 0. So I can just say that the massive black hole at this time, I'm going to call its mass m. I can say that its angular momentum is 0. I can say that its angular momentum is a little bit negative, and then it's absorbed a little bit, and so that moment its angular momentum is 0, so swash all the whole black hole. And I can say that the orbital frequency is precisely omega 0. That's the free choice I have at any specific time. Now later on, of course, these things will evolve, so I can't do that at all times, but just at one instance I can. That slightly simplifies the equations, and so that's what we do. And so for the rest of the results I present, we make this choice. But later on, when we want to actually compute waveforms, we're going to have to relax that. Okay. And then finally, then, how do we construct the regular field? Well, as I said before, this isn't too hard. We have some source. This is an ordinary differential equation. It's a second order ordinary differential equation. We just use variation of parameters. That's what we did back in first year. There's obviously some details. And so this was actually the talk. This is a slide of a picture from the talk I gave here 5 years ago, where we kind of laid out how to do that at first order, how to compute these punctures, the equivalent thing at first order, and how to actually solve for the metric perturbation in this fashion. You have to do it this way because you can't, at first order, which is what's shown here, you can just compute the retarded field and subtract off the puncture exactly of the particle. But you can't do this at second order because you have a divergence at the world line. So you have to use these puncture effective source methods. Okay, so those are all the pieces. I appreciate that as a flying overview. There's a lot of detail there, but hopefully you've got a flavor for the pieces that are required and how they fit together. So we've computed this second order source, the effective source. We've then performed variation of parameters, and we can now compute the regular metric perturbation. So the very first result then that we just did this for the monopole mode, the L equals 0 mode of the metric perturbation. So this is an example of that. This is a particular mode, tensorial mode, the I equals 3, it's not important, but it's the monopole mode. And here what I'm showing is, in blue, the retarded metric perturbation, which you can see is diverging logarithmically at the world line. And then in regions around the world line, I have to apply these punctures. So, but inside that puncture, the divergence has been removed, and I have something smooth at the particle, which then means I can take a derivative and compute a self-force, for instance. There's also some punctures near the horizon. Those are those things I showed earlier to deal with the problems at infinity, problems at large scales. So near the horizon, and also there's another one out here in infinity. Okay, that's very nice. I have the metric perturbation in some gauge, Lorentz gauge. Very good. What do I do with that? Well, this has been a very long calculation, and so the first thing you want to do is make a comparison with someone else. Like someone must have computed some other quantity that we can compare against. And so we chose, rightly or wrongly, it ended up being a lot of work, the gravitational binding energy of the binary. Because we thought we know other people who've computed something with the same name at least, we can compare with that. And as it will turn out, the fact that these two things have the same name doesn't mean, of course, they're the same thing. So that slowed us down a lot. So what we did, we computed the binding energy. Well, that's just the difference between the energy of the binary versus the two constituent pieces. So in GR, that's the bonding mass. And then you subtract the difference between the perturbed mass of the black hole, as measured from the perturbed invariant horizon, and the mass of the smaller black hole. And then notice here I'm just normalizing by the reduced mass. So in our expansion in the mass ratio, we can write that out explicitly. We can write the binding energy as some leading order piece plus some self-force correction. And this self-force correction is dependent upon second order in the mass ratio pieces of the metric perturbation. And we compute these directly from the plot I just showed you before by just computing the value of the regular metric perturbation at the horizon or at infinity. Now some of you might notice, how is this, what's happened here with my order counting? I have an epsilon here, done an epsilon squared, well I've normalized by the reduced mass. So this really is a second order quantity. Okay, so why do we do this? Well, we wanted to compare against something, and there's this other thing called the first law of binary mechanics that allows you to compute something which is called the gravitational binding energy. And so we thought, great, we'll compare with that. So the first law of binary mechanics is a way of relating the changes in the Bondi mass and angular momentum to local quantities, the changes in the masses, and something called the redshift, the Detweiler redshift invariant. It's similar in flavor to the balance law, which relates second-order fluxes to first-order self-forces. The first law of binary mechanics relates the binary's second-order energy at infinity to this local first-order invariant. And you can write this out explicitly in terms of self-force quantities. So this ZFS is something we've been computing in the self-force community for a decade now. This last line is very crucial. That this law, the derivations law, makes some key assumptions. It assumes that it's in a conservative space-time, which is helically symmetric and asymptotically flat, which is not consistent. You can't be both of those things at once, but that's what they assume to derive this law. Now, they've made comparisons with this against numerical relativity, and they find it does very well. And as you will see, we also find it as well, but we don't get perfect agreement. Okay, so this is the main big result. So from that metric perturbation, what we're able to compute is the following. So here, what I'm showing is the binding energy, either computed with the first law, the blue line, or using our second-order results directly from the second-order metric perturbation. On the x-axis, y is some measure of the radius, the usual invariant radius used in PN theory. Out here, this is larger radius orbits, the Newtonian regime. Here is the innermost stable circular orbit of 1/6. Let me go a little bit below that. And what you can see is that there is some level of agreement. It certainly looks like they're doing the same thing, but there is some disagreement in the strong field. When we first got these results, we were very excited to see this level of agreement. We didn't have error bars. And we thought, great, hopefully the error bars will be so big that they will encapsulate the line and we can say they are consistent. Now, unfortunately for us, we produced some quite conservative error bars, and our error bars are sufficiently small that we can say that there is a difference between our result and their result from the first law. And for a long time, it took us a good year to kind of really deal with that. We weren't really happy not understanding this problem. And I think we were really misled by the fact they have the same name, is what I would say. We really felt they should agree, but as you look at more closely into the assumptions they were making, you could see they were different. So for instance, through our 2 timescale expansion, our binary, we are encapsulating the fact that it is inspiraling. They don't have anything like that in their calculation at all. So you would expect them to disagree at some order. So the question might be then an interesting one, well, what order would you expect them to disagree at? How can we quantify that? And so one way to do that is to look at the post-Newtonian expansion, the first law result, and compare it with ours. So what we can do is we can take our result, which is these blue dots, and then we can take the leading order term in the PN expansion, which is the blue line, and if we subtract them and then something is subdominant, then we say we have agreement. And that's precisely what we find. We subtract the blue line from the blue dots of those values, and we get the yellow dots. So we agree with them to 0 PN. Well, we can continue this game and subtract the yellow dots from the yellow line, and we find we agree them at 1 PN, agreement at 2 PN, and at 3 PN, we also seem to find the dots are lying close to the line. Unfortunately, our data does get weaker, get less accurate at large radius, which is precisely when you'll make this comparison, but it looks good. You then can say, I'm going to take our data and subtract off the 3 PN term, and initially it kind of looks okay. It looks like this line is tending towards the 4 PN term, but this is the absolute value of this quantity, and it turns out that these two things have opposite signs. Not exactly opposite, obviously that would be great, but not sufficient. So we know there's a discrepancy at 4 PN between the first law of binding mechanics and our result. That is perhaps not completely unexpected. At 4 PN is where hereditary terms enter this quantity, and these hereditary terms are related to what's happening in the past, and we are inspiraling and they are not. And so it's not completely unexpected. Now, we don't have a deep understanding of this, but it's consistent with where you might think the discrepancy would appear. We'd also like to compare numerical relativity, but the data we can have access to in numerical relativity is probably not accurate enough at the moment to make that comparison. We're computing the second order in the mass ratio term. We need to make an NR simulation at a small mass ratio, and that's very difficult to do with high precision enough to see the difference. Future work. Okay, so as I said, that was a flying overview. There are many, many details given out in papers. So the original foundational papers by Adam, the actual expression for that second order puncture by Adam and Jeremy in covariant form, some ideas about how I can compute conservative quantities, some practical methods developed by myself and Barry for actually making these calculations, dealing with these problems at large scale, dealing with these infinite coupling problems. These are all laid out in these papers that appeared over the last 5 years. And then just now, this result, as I say, has just been accepted into PRL last week. And there's 2 more papers coming, one giving the details of the 2 timescale expansion, and also discussing the coupling formula that Adam's been working on for a while. And there's at least two more that we're still to start on. So there's a lot of results and theoretical underlying all this. Great. I mean, so what I've showed you there is the L equals 0 mode of the second order vector perturbation. It's been a long slog, but we have it and we've computed something and it looks good. We have some agreement with something. There is some disagreement, but perhaps it's not unexpected. Okay, so what about the higher modes? This is what we really care about. What I really want is the dissipative piece, so the L equals 2 and above. Like, how do I get hold of those? So where are we with that? So as I mentioned at the beginning, all the machinery we put together basically works for arbitrary modes, but we just concentrated on the L equals 0 piece. So since we put that paper out in August or September, we've already computed these 2 terms for the higher modes, so the puncture and the slow time derivative terms. So then the only piece that's remaining is this. So as I said, we can expand this out into products of the singular piece, singular, regular, and regular, regular. We've computed these now, these 2 terms. This is a plot of these for the L equals 2 mode. There's a divergence at the world line, discontinuity of the world line, just for some piece of this. The last piece we have yet to compute is this. It turns out to be rather difficult to make this calculation, just doing the mode decomposition. The equations are just vast. The problem is mostly Mathematica crashing. It can't handle it. So you need to break it up into smaller pieces and then tackle it that way. But even at this level, we have checks. So these punctures, there are pieces of the puncture here that correspond to dealing with this. And so we have just 2 weeks ago, what we can do is we can subtract the puncture off that's relevant to these 2, and we know that what we should get is something which loses this discontinuity, but is C0. And when we do that, that's exactly what we find. So that's already a pretty impressive test, because there's huge amounts of machinery and calculation that have gone into computing these things analytically, these things via numerically. There's also things that are cancelling in here. So we see huge amounts of cancellation that we expect in the calculation, so it's very promising. And in fact, if we had this piece, if you gave it to us tomorrow, in a week or two, we might have the full second-order metric perturbation. That's how close we are now. And Adam is visiting us in Dublin next week, so we're hoping to make some more progress. Okay, so the last thing is then just how do we actually compute an inspiral? Maybe interest people who interested in the numerical side and even the data analysis side, because the parameter space grows slightly. So let's just review how you compute an adiabatic inspiral. So you pick some R0 at some time, and from that you then compute the orbital frequency, just in the way we used to expect. And then you go ahead and solve the first order equation, right? If you want, you can do this with Tucholsky, Reggie-Wheeler, whatever you want. And from that, you extract the fluxes, and that tells you how R0 changes as a function of time, right? This is the usual quasi-circular inspiral. And then to compute an inspiral, we just loop this process around, right? This tells us how this changes. We then go back, we update this, we can recompute it. Of course, in practice, we'll tabulate things, and we won't run a loop like this. But that's how it would work. To compute the waveform, then, we just integrate omega against the time to give the waveform phase. And sorry, to get the phase, and then to get the waveform, well, we have that everywhere. We've solved the metric perturbation, so we have the waveform. As second order, well, now we pick an R1 at some particular time. From that, we can compute the perturbation, the correction to the frequency, which has an input from this first order metric perturbation here through the first order conservative self-force. We then go ahead and solve the equation I've been spending most of this talk talking about for a particular value of R1 and R0. And then that tells us how to compute the second order dissipative force, and then in order to compute an inspiral, we loop that around as well. One thing I haven't mentioned here is there's also delta M and delta J. So the mass, length, and momentum are also varying. And so if you want to fill out a parameter space for a quasi-circular inspiral, you have to, at adiabatic order, you just need to have R0, but at subleading order, your parameter space has grown to 4 dimensions. You have R0, R1, delta M, and delta J. So already that's become a bit more difficult, because now you want to fill a parameter space, you've got to interpolate that. So there's a challenge there. Just to finish off, if you want to compute sorry, I forgot this. You want to compute the actual waveform phase, well, we just have omega 1, so we just integrate this again, and then we get our second order accurate waveform. So that's the procedure. And I think we're close to doing that, though not quite. So what's the timeline? So I've told you, pretty soon I really expect we're going to have the second order metric perturbation. So as I said, what we have managed to compute is the monopole piece. But this really encapsulates most of the techniques required to do the second order piece. So tick, that's done. As I said, many pieces are ready for higher modes. So what are the next steps? So we expect within the next 3 months to have the 2-2 flux, or the 3-3 flux or whatever, but the 2-2 is the flux we'll certainly be able to compute. But for this, we will have set delta M, delta J, and omega 1 to 0. So though we'll have this flux, we won't be able to use it to compute an inspiral, because at each instance we've chosen what the mass of the black hole is. We haven't tracked it through the evolution. We have to turn back on these terms in our calculation and run it again. They're not particularly complicated, but we're just trying to simplify things as much as possible in a complicated calculation. On the order of a time frame of less than a year, we'll be able to turn these things back on. I think a year might even be generous. And for that, we'll be able to compute a full quasi-circular inspiral, including the waveform, in Schwarzschild. And because when we do this, we get the whole metric perturbation, we can also probably compute conservative quantities, like the dead-Weiler redshift invariant to second order. And so just to bring it back to what I talked about at the beginning, well, this is potentially really exciting, because what you'll have is an error that scales as order epsilon. And so again, it really depends on what that coefficient is in that term. But if it's small, if it's 1, then at mass ratio 1 to 10, I will get a phase error of a tenth of a radian. Now, we don't know what it is. I make no claim to know what it is. It might be huge. It might be tiny. But it'd be really exciting to compare this stuff with numerical relativity and see how much of the parameter space can we cover using this perturbative nonlinear approach. And what's the more longer-term outlook? So that was for quasi-circular orbits in Schwarzschild, so nothing is spinning. So this really represents the end of the beginning. It's taken a while, but we now really understand the foundations of how to do second order, and although when we were facing it, it was scary, in hindsight, it doesn't seem so bad, right, as always. And so there are obviously a lot more to do. We need to incorporate finite size effects as spin on the secondary. We need a practical methods for solving things in Kerr spacetime. This is one of the big open challenges. So far, everything we've done is in the Lorentz gauge, and we don't know how to decompose the Lorentz gauge in Kerr spacetime. We just don't know any spheroidal tensor harmonics that can do it. Well, great, we do know ways of doing things in Kerr. We can use Stokowski, right? That's very powerful. But remember, we need to compute the actual metric perturbation, so we have to go through the metric reconstruction procedure. But this is only known how to do this in vacuum. But we're not in vacuum. We have the first order metric perturbation there. So development needs to be done there. There's some progress recently, but that would be a great way forward. We also, of course, need to extend things to eccentric orbits. But as it says here, significant human effort is required to do this. And so perhaps putting my hat on as someone who's involved with the LISA consortium, we really want more people to work on this stuff. And we feel like it's not so scary anymore because we know how to do these calculations. And a key part of this will be another project that I'm heavily involved with is this thing called the Black Hole Perturbation Toolkit. So if you want to solve second order metric perturbations, you cannot be writing first order codes. You need to be able to pull that thing off the shelf, pull that data off, and use it. If you want to get a PhD student, I have students working on second order stuff. If they had to then write all their first order stuff, they would use up their 4 years before they got any second order stuff done. So this is a project which you can go to this website, bhptoolkit.org, and there's free open source Stokowski codes, data, quasi-normal mode codes, all manner of things related to perturbation theory. We're trying to bring that together in the community to solve these problems. So I'll finish there. Thank you.